Hello everybody, welcome to the December Symposium presentation for the Battery Event Safety Alarm Fixture, or B-Safe design project, sponsored by EaglePicher Technologies. Our two technical directors for this design project were Dan Norick, the Senior Electronics Engineer at EaglePicher, and Daniel Wirtz, the Senior Systems Engineer at EaglePicher. This team is constructed of 4 URI seniors, a part of the ELECOMP Capstone program: Jacob Muller, Sarah Arribas, Christopher Conklin, and Joshua Manasian. EaglePicher Technologies is a leading producer of batteries and energetic devices. For more than 75 years, they have been serving the mission-critical aerospace, defense, aviation, and medical battery markets. Their batteries are key components of the United States space program, and they provide the emergency power that successfully brought the Apollo 13 crew home. Today, their batteries power the International Space Station, Mars rovers, commercial jets, helicopters, countless life-saving medical implants, and more than 85% of the United States missile platforms. As batteries become more complex and possess higher voltage capacities, EaglePicher recognized the hazards that they possess. They decided that they are committed to providing the safest possible environment in the manufacturing of these potentially dangerous batteries. The DC voltage of a charged high-voltage battery creates some potentially deadly hazards when immersed in water, and there are challenges in detecting the presence of these hazards from a distance. While live AC power lines can be detected from a distance by devices often carried by first responders, DC fields do not propagate through the air and require a different means of detection. The motivation of this project is to determine if an effective method for detecting these hazards exists, and if so, developing a device to provide an early warning for such hazards. The anticipated best outcome is a prototype of a device that is capable of detecting dangerous conditions in water caused by a high-voltage battery, and then taking that information and providing a warning notification when dangerous conditions are met. This device must be able to operate in both tap and salt water and be able to detect danger without a common ground voltage reference. This notification for the user will be given from a distance to maintain the user's safety. The ideal outcome would be a portable device that is usable by first responders to detect the presence of a shock hazard when responding to a drenched or submerged battery. The key accomplishments the B-Safe team has made towards the ABO can be broken up into 4 phases. The first phase is initial research, where information was gathered from various sources regarding the resistance of a human, existing battery voltages on the market were compiled, physics of electric fields were researched, and existing DC current detection technologies were consulted. This all went into the initial mathematical model of the scenario and was used to determine a possible solution to detecting DC electric fields from a distance. In Phase 2, a simulation of a scenario was constructed. A power supply was set at various voltages and had its leads submerged in tap water and simulated seawater, so that measurements of both voltage and current could be taken at predetermined intervals to find the voltage and current distribution in the water. Human resistance was also measured with having volunteers submerge their hands and feet into water and connecting it to an ohm meter. This was determined to be, on average, equivalent to a 2.7 kilo ohm resistor, which was then used to find current at various distances from the source. After completing the simulation, the third phase began, which was mathematical modeling. Using the data obtained from the experiments, the scenario of a high-voltage DC source immersed in water was modeled using MATLAB to visualize the experimental data and to extrapolate and determine a risk radius in a real-life scenario. Finally, the fourth phase began, the preliminary design phase. A prototype and a bill of materials were designed, which used a Raspberry Pi Zero W as the primary microcontroller, an LED strip to display the risk level, and an analog/digital converter to convert the sensed voltage to a digital value for the microcontroller to use. A voltage regulator was designed to isolate the sensor voltage from the internal A to D converter to prevent it from completely damaging the device if it does encounter a high voltage across its probes. The voltage regulator will automatically determine a dangerous condition if the voltage becomes high enough to be needed. With the team meeting our best anticipated outcome of deploying a battery monitor, EaglePicher would have a solution to detect shock hazards near a high voltage battery in a body of water. This will allow EaglePicher to eliminate the risk associated with fabricating high capacity batteries. If successful, the deployment of the battery monitor will result in no accidents, injuries, or loss of time and loss of revenue due to unseen or undetectable shock hazards in the manufacturing of large dangerous batteries. Creating these enhancements to safety in the battery industry will stimulate growth by eliminating risk associated with manufacturing and handling these large high voltage batteries. Here you can see a block diagram of the overall battery monitor. You can see the energized water interacting with the A to D converter, which interacts with the Raspberry Pi, which outputs to the user interface, which in our situation would be the LED strips which are lighting up. My name is Joshua Manasian. I am an electrical engineering major as well as a mathematics and psychology minor, and I will be discussing with you my personal accomplishments with this project. I contributed a large part to the initial research phase, or phase 1, of the project. I was crucial in determining a value for current that poses a danger to an individual. This value was determined to be 17 milliamps after researching through multiple sources as well as government-approved documentation. Also, a determination was made for the common conductivity ratings for common sources of water, which were crucial in the later mathematical modeling stages where a risk radius was determined. A human resistance value was determined, approximately 2,500 ohms. The value for human resistance, though, is subject to change based on the makeup of the individual's skin, if they have any scar tissue, if their hands are wet, if they are submerged fully or only partially, or if they are wearing anything over their hands. Using these two values and Ohm's law, I was able to determine a necessary voltage that an individual would need to feel under DC voltage, which is approximately 40 volts. I also compiled a list of all batteries used on the market for electric vehicles to determine a realistic scenario of what an individual would feel in a first responding situation. I also assisted in the second phase of the project, the experimental testing phase, where I assisted in the construction of a large texting fixture with fellow designer Christopher Conklin. I then assisted, as well as with the rest of the team, recording data points from various experiments using that testing fixture. I was then part of the team that analyzed that data using MATLAB from that experiment. Overall, the data allowed us to determine what would happen if an individual was grounded or not grounded inside of a pool of water to a battery. We were able to determine that on average, if an individual was grounded, they would immediately experience pain while entering that pool of water. Differentially, the measurements we received when an individual was not grounded were considerably lower in magnitude, but followed a similar trend to when an individual was grounded to a battery. We decided, using this information, that our proof of concept or prototype device would have to record the differential measurement, as this was most common in a scenario. It is also important to note that when I refer to grounded individuals, I mean when an individual is connected to one of the ends of the terminal of the battery. The first experiment done in tap water was done with a 300 volt DC power supply, outputting 400 milliamps of current. As you can see from the graph to the right, we experience a high of 152 volts and a low of 136 volts. I theorize that the slope of the overall 3D graph is due to the fact that the water itself was on an uneven surface because the floor was not even. In this graph, we utilized salt water instead of tap water. Although the power supply did have an upper limit of 300 volts DC, it was only possible to output 85 volts DC due to the fact that the power supply limited itself after outputting 17 amps of current. The fact that this scenario outputs so much current is most likely due to the fact of the conductivity of the salt water that mimicked seawater. The key accomplishments that I will be contributing to this project by April include the construction and finalization of the proof of concept device, as well as the completion of benchmark testing and field testing of said device. The team will then begin construction of the first prototype based on the proof of concept device, and once that is completed, increased functionality and runtime will then begin to become a major factor in our design, as increasing both of these will make our product more widely accepted by the industry. I would now like to turn things over to my fellow electrical engineering major, Sarah Arribas, so that she can discuss her own technical contributions to the Be Safe design project.
Much of my work consisted of dealing with the physics perspective of the problem. So in the overall picture of the scope of this project, my work dealt with the energized water block and what would be expected to be sensed there. Using the research conducted by Joshua Manasian and Christopher Conklin for resistivity values, human resistance, and battery parameters, I created an initial mathematical model of the submerged battery scenario. By modeling the leads of the battery as a dipole creating an electric field, I was able to create a function of the expected resistance from the water to a person at any given point away from the battery using the path length of the field. With this function, based on the current levels that would affect a human, I found a preliminary risk radius we would need to work with. Approximately 70 meters away would be where one would expect to feel pain, and 15 meters away would be lethal. During our experiments to simulate a human in electrified water, I helped to analyze the data from the experiment and create a 3D map of the voltage we measured in MATLAB. Pictured here is our first 3D map of the voltage when we set our power supply to 50 volts in water and were measured with respect to ground. The contour graph at the bottom shows a figure similar to what we'd expect to see of an electric field created by a dipole. Amidst these experiments, we brainstormed ways to create sensing devices. The magnetic field seemed the most viable parameter to test safely, so I calculated the expected magnetic field to be measured at a safe distance away. I also researched into the strength of Earth's magnetic field to compare, and I looked into how Hall effect sensors work. It turns out the magnetic field would be 30 times weaker than Earth's magnetic field, and a precise enough Hall effect sensor only exists as a bench testing device, and is therefore not portable or helpful here. Since their sensitivity relies on doping methods in the sensor, it would be infeasible for us to accomplish. With all the data from our experiment, I recreated the mathematical model, both with the human in parallel and in series with the water resistance. Using both the max and min values of human resistance, I plotted the expected current at various distances. While both showed the variations in human resistance we found were negligible, they also show very different results in risk radius. The series model showed it could be dangerous out to 150 meters in seawater, and the parallel model showed it not to be dangerous at any point besides directly touching the battery terminals. By April, I expect to help with completing the proof of concept design and helping in its testing. My main focus will likely be data analysis, such as observing the readings from our device and interpreting them and how they can be improved. Because of the wide range of scenarios this device may face, I will also help in designing added features to the device to improve its accuracy in more conditions. For example, the voltage seen across two sensors on the device can easily be determined for safety. However, it cannot predict how much farther it will be safe for, because that depends on several factors. With sensors for these parameters, it may gain the ability to make such predictions. These are also considerations for the preliminary design for a prototype. One of the challenges we will face with the prototype is keeping the internal circuitry safe from water. We plan to make some sort of waterproof and buoyant structure for it to work within. Without further ado, I would like to introduce our next speaker, Christopher Conklin, to discuss his contributions to the Be Safe project.
Hello, ladies and gentlemen. I am Chris Conklin. I will be focusing primarily on the load portion shown in orange on our block diagram and the A to D converter shown in the large green outlined area. Some of my key accomplishments to date are doing research on human DC resistance while standing in water. Our initial research, we determined that the human resistance should be somewhere around 100k ohms, but this was very wishy-washy because most of the research done is with AC. I also looked into the highest possible voltages that could be encountered, which would be somewhere between 350 volts and 1000 volts DC. Because of the inconsistencies in the initial research for the human resistance, we decided to do our own testing with people standing on metal plates while submerged in water. We measured their resistance and we determined that to be around 2.5k ohms. I also constructed two boxes. The first box is shown in the photo below, and a larger box which was 8x8. Did testing on those boxes at 60 volts and 300 volts. Lab setup and testing was done numerous times on numerous occasions, in both at URI and EaglePicher. Some of those initial testing apparatuses were a little overcomplicated, and with the help of our TD, Dan Norick, they were simplified. I also worked a lot on the proof of concept design, testing the evaluation board, setting the parameters for that evaluation board, and the preliminary circuit design, which I will go over next. Here we can see the first iteration of our overall schematic using the ADS 131 from Texas Instruments. It is then connected to a Raspberry Pi. The ADS 131 is getting its input from 3 different load sources. In this iteration, it is a 2.2k ohm and a 200 ohm resistor. That was later found to not work as well. We have since gone to a 2k ohm and a 400 ohm resistor, taking the input across the 400 ohm resistor. Here we have the ADS 131 evaluation board hooked up to our load. We have a power source of a single AA battery. We initially had it hooked up to a power supply, but we got a lot of noise out of the power supply. So in the interest of setting up our baseline parameters, we've moved to the battery. There's also a capacitor installed across the 400 ohm resistor in order to reduce noise to the input. To the right, you can see some of the initial parameters. This is a 32-bit A to D converter, but we've lowered it to 16 bits, again, to compensate for noise, with an oversampling rate of 8,192 hertz. Goals to be completed by April include finishing the proof of concept design, testing that design, and possibly start prototyping off of that previous design. Include any added functionality, packaging, and a power source that we might require. Our next team member is Jacob Muller, a computer engineering major who's also minoring in digital forensics and mathematics.
As the sole computer engineer on the EaglePicher Be Safe team, most of my individual contributions will include preliminary testing, researching hardware, and assembling the software and programming parts of the project. These aspects are vital for the creation of the proof of concept and eventually the prototype of a device that detects hazardous conditions in water. A significant amount of time this semester was spent conducting preliminary testing to understand the dangers that occur when a battery is submerged in water. During these tests, I was able to take voltage and current measurements with a multimeter, which were analyzed and used to determine if an individual would be harmed by the surrounding water. Understanding the voltages at which human injury and fatality could occur is important to know when designing and creating a safety device. I need to use the data and analysis from our tests to determine the values that trigger our device to warn an individual. After coming to the conclusion that finding voltages is the best way to determine the safety of the water, I conducted research on parts that will be used on the proof of concept and eventually a final prototype. The first part I researched was microcontrollers. At the time, I was not sure what kind of capabilities would be needed for the concept or prototype, so I determined that using a Raspberry Pi would be ideal. The particular one I chose is the Raspberry Pi Zero, a model that incorporates Bluetooth and wireless capabilities in a small footprint. The device's size also makes it easier to package for a prototype. I also prefer to program using Python, which was a factor in choosing a device. The other device chosen was an analog to digital converter, or ADC. This is necessary because the Raspberry Pi will not read an analog input. The ADC is capable of taking voltages and converting it to a digital output that can be read by the Raspberry Pi. The ADC chosen is a 24-bit 4-channel evaluation module manufactured by Texas Instruments. This particular ADC is low power, simultaneously sampling, and is able to communicate with the Raspberry Pi via Serial Programming Interface, or SPI. Shown on this slide is a flowchart of our proof of concept. Sensors in the water will be connected to the ADC. The Raspberry Pi will collect voltage data from the ADC via SPI after it has been converted to a digital value. When the Raspberry Pi detects a voltage that is considered hazardous to a human, it will alert an individual through the LED strip. Not included in our proof of concept, but shown on the flowchart, is the wireless communication to a device via Bluetooth. This is a function we would like to add to the final prototype. My personal technical accomplishments next semester will include writing the Python script on the Raspberry Pi Zero for the proof of concept. After writing the program and assembling the proof of concept, it will be tested to ensure it is fully functional. This may include having to modify the Python script. After the proof of concept is complete, I have to construct the prototype and include the use of new features, such as Bluetooth communication to send warnings to a user's device from a safe distance. Once the prototype is complete, I will test the functionality of the device to ensure it can read voltage measurements and successfully transmit alerts wirelessly to another device. Our team's future accomplishments toward the best outcome include building a proof of concept. Using the design created and the parts chosen this semester, we will assemble the functional proof of concept next semester. Once this proof of concept is fabricated, it will need to be bench tested for functionality. The proof of concept will be tested to determine if it can first discern a safe voltage from an unsafe one. Then it will notify the user of an unsafe condition using the LED strip. Once testing is complete, we can plan and design the final prototype. For the prototype, we need to create a suitable container to keep the device's sensors in water while protecting the device from water so it is not damaged. The design should allow the device to be buoyant, making it easy to throw and retrieve in water. Similar to the proof of concept, the prototype will have to be tested for functionality and in various conditions such as tap and salt water. Our future technical accomplishments also include design improvements, which will be necessary for our final prototype. This includes adding Bluetooth capabilities to allow communication with the user from a distance and be more widely accessible. Adding this capability means we also have to create a graphical user interface for an application. This application will connect a device to the Raspberry Pi via Bluetooth that provides a clear indication of danger to first responders and utility workers. A Python script must be written and applied to the Raspberry Pi Zero single board computer. When the Python script runs, it should read the voltage from the ADC. Then, based on the digital input, warn a user of unsafe conditions by lighting the LED strip. With the collected data, some improvements to the design have been envisioned where the device can calculate how much further the zone will be safe for the user. It may include built-in salinity or depth sensors, and a revised program to help make those determinations. The EaglePicher Be Safe team would like to thank all our technical directors at EaglePicher and the University of Rhode Island. We would like to give a special thanks to Daniel Norick at EaglePicher and the ELECOMP Capstone director, Dr. Sunak, for their guidance and support on this project. Thank you.